Hello all, and thank you for watching our video on our Group J concrete pump system. Myself, Adam Lazine, my partners Colin McKee and Tyler Richmond will all be presenting our system in group assignments.
In this presentation, we analyze a system designed to transport concrete from a concrete truck into a hydraulic pump that goes up 100 feet. The analysis draws on principles and equations covered in class as applied during project sessions 3, 4, and 5. Shown on the slides is a diagram of the steady state flow as the elbow at the top of the pump dispersing out. The density of the concrete remains constant throughout the whole entire system as 2,300 kilograms per meters cubed. As shown, we have solved for the area before the bend as A1 and the area after the bend, A2. Using the initial area and velocity, the volumetric flow rate is obtained. Using the volumetric flow rate, Q, we can solve for the exit velocity, V2. After solving for these variables, we can solve for the mass flow rate, and that is 1,168.4 kilograms per second.
Project sessions number 4, work energy equation. Now we first drew a diagram of our system, which you can see the EGL highlighted in blue and the HGL highlighted in pink, as well as I'd like to note that the horizontal datum is located around point 2 at the bottom of our worksheet. Next, we use the work energy equation to eliminate the known variables or unknown variables. We were able to eliminate P1 because of an open channel, V1 due to the larger reservoir in the concrete truck, P3 due to a free jet, HE due to a lack of turbine, and HL because of no head loss. With these variables eliminated, we were able to um, confirm an equation of Z1 plus HU equals Z3 plus V3 squared over 2G. Using calculations from previous group work, we were able to fill these variables with known values, resulting in a calculated HU of 50.2608 meters. Using our new HU value, we were able to calculate the horsepower of our pump, which we were able to calculate at about 107 horsepower. After doing a little research, we found that a large commercial concrete pump had about 350 horsepower. And using this new horsepower, we were able to calculate the efficiency of a commercial pump at about 31%. Noticing the discrepancy between the commercial horsepower and efficiency and our calculated horsepower and efficiency, we realized that this was due to the lack of head loss in our system, which is to be expected.
To solve for the impulse momentum equation, we used a portion of the system that had a 90-degree angle, which is located at the top of the concrete hose just before it pours out. After finding the section, we rotated the axes to have the y-axis in the vertical direction and the x-axis in the horizontal direction. And using this part of the system, we found the velocities, areas, volumetric flow rate, and the specific gravity were all found in previous group assignments. We just needed to find the resistance force in the x and y direction acting on the bend. We started by finding P1 using the Bernoulli's equation, and because we used equal lengths on each side of the bend, the z values canceled out, making the equation easier. We moved on to the sum of the forces. Since the P1A1 value in the x direction is moving to the left, it's negative, and the resistance force is moving to the right, it's positive. In the y direction, the forces, the P1A1 is moving up, so it's positive, and the FR is moving down, so it's negative. Then the momentum expressions, since the x axis only has an output, the v2 is positive, and since the y-axis has an input, the velocity is negative. After combining the two equations, we are able to find the resistance force in both the x and y direction. Knowing those values, we can solve for the total resistance force, which can be found by the square root of the sum of the x force squared and the y force squared.